What I mean is we're not going to look at the middle of the rod. We're going to look at a point that is aligned with the end of the rod. And we're going to ask ourselves, what is the, and we'll either fill in the blank here, electric field or electric potential at that point. So this is considered a distribution of charges. We're going to say that the rod has a uniform charge distribution. So before I even kind of get into the weeds of that, remember that you're looking at whether your charge distribution is a linear charge distribution, a surface charge distribution, or a volumetric charge distribution. And the symbology that they're supposed to use for each of those should be one of these three characters. So lambda is used for a linear charge distribution, sigma is used for surface, and rho is used for volume. That's the general truth, whether we're talking about charge distribution or mass distribution. That's what they tend to use. I'm doing more than I think I should, but linear would be coulomb per meter. Surface would be coulomb per square meter, and volume would be coulomb per cubic meter. So we're looking at a clear linear charge distribution. And whether you would use the symbol lambda or not will depend highly on what they give you here. They can tell you that the object has a charge distribution of lambda and not give you the total charge. That's especially true if they give you an expression for lambda, something where the charge distribution isn't constant. So before we even start the electric fields portion of this, consider a case where the rod is of length L and has a charge distribution of A times X, a linear charge distribution where the strength of the charge increases as you go from one end to the other. Under this particular example, we wouldn't even have the total amount of charge here. Now, we're not going to execute this fully, but I think that there's a pretty large number of you in the room who wouldn't be able to tell me how much is the total charge of the bar. So let's do a problem before the problem, dealing with what happens if you're given a charge distribution that is not uniform and you're asked to figure out how much charge there is. First, before I even start that, what must the units for A be in this particular expression? In the modern AP exam, they're likely to say to you stuff like A has units of coulombs per meter squared or something like that, especially if they're going to put numbers to the problem later. But I think it's reasonable to expect that that's not just fluff. They're trying to provide you with some rooting in what they've given you as an expression. So that's what I'm trying to do. What we're about to do now are the beginnings of how you would do the electric field portion, but in a far simpler case. The first thing I told you guys that you should do in any problem involving a distribution of charge is to identify a portion of the total charge. So just someplace on the object, choose a length, an area, or a volume. So I'm usually talking about choosing a small piece of length, a small square, or a small cube of the object. Since we're unlikely to do three-dimensional objects that don't have a certain amount of symmetry, we usually stick with just lengths and areas. So I'm going to identify just a piece of the object right at the very beginning. And I'm going to say this is a piece of length. It is dx long. And I can point to it by choosing a distance x away from 0. I'm looking to describe this piece geometrically, because that piece has charge dq. It has a small amount of the total charge. So every time you're given a charge distribution, your first job is to pick out a piece of the charge and label it. Give it a physical label. I draw the picture because we use the picture to help us identify portions of our problem. Now, the next thing you have to do is identify where that part is, which is what we did. I'm saying that this piece lies a distance x away from my origin. And then describe its size. This piece is a little more in the x direction. So 3 things you have to do just to get started in any of these problems. Identify a piece of the charge, label it dq. Find a way to point to it using some kind of coordinate system. That's the hard one, and one most people don't understand, and once they don't understand this, they never get it. So I'll say it again. Find a way to point to it by choosing a coordinate system. There's 3 things that you have to do underneath there. You have to decide where is 0 in this coordinate system. Point of reference. So assign something 0. I could assign anywhere I want to be 0. I'm using a place that makes sense to me, one end of the rod. And then once you have assigned your reference point and you have decided whether you're going to use Cartesian, x, y, and z, or say polar, r and theta, or spherical or cylindrical, once you've decided, see if you can point to every single object or every single part of the object using your decision. Can I reasonably point to every piece of the bar if I assign 0 the left end and use x as a location or a pointer to each piece? Well, obviously I can. Right? X can start at 0 and go to L. Next, since the first question was just finding out the total charge, remember, we have identified what we call a piece of the charge. The total charge is just the sum of all the pieces. That's going to be true for all of these. We are summing over a piece of the charge and what the effect that piece has on our system. So summing up dq just gives you q, the total charge. So if you want to know how do you find out what the total charge is, you're going to integrate, you're going to add. You're going to add a contribution to the charge from each piece. Now, we can't just add this up and go from 0 to q. That's not how this works. Each individual dq is adding a different amount of charge because as I go from one end to the other, the charge density is increasing. So if I want to find out the total charge, I probably need to find a way of expressing that charge in terms of the location. So that's where you start looking, is there a way for me to transform dq into something about the geometry? So that's kind of the second big step. Once we've identified what dq is and we can point to it, the second step is, can you write dq in terms of your geometry? And the easiest way to do that is to recognize that dq is going to equal charge density times time. I'm leaving it generic. If it was 2-dimensional, that would be sigma times dA, where A stands for area, a piece of the area. If it was a 3-dimensional object, it would be rho times dV, where V stands for a piece of the volume. We have a linear one, so it's going to be lambda dx or dr or dy or whatever you're using as your linear variable. So now we do substitution. I replace dq with something that represents dq in terms of the position or the size. So lambda dx. We have an expression for lambda, luckily. So we can plug in that expression here. So and once we feel like we have a complete expression, you should be able to tell your integral where's the first piece of charge and where's the last piece of charge. Now, this one's not particularly interesting, but this is how you would find an expression for what the total charge is of your system. And it's not exciting, but you can do this calculus. I don't want to spend time on the calculus. That's to get us set up for the problem. We all okay so far? Any issue with this? Yes, sir.
I don't get the emphasis on.
Again, I'm not sure exactly what your question is, or I'm not exactly sure how to answer your question. I'm going to do my best. In this particular instance, we are taking our object and breaking it up into individual pieces of charge that we are labeling dq. So we are introducing dq into the problem on our own, knowing that in the future, our answer is not going to have dq in it. We're going to get dq out of the problem. We're using it as a physical representation of a single point charge. The idea is that if we add up all the point charges, we will get something about the effect of the point charges on this region of space. Either their electric field that they create, the electric potential that they create, or in this case, the total charge related to that piece of charge. And it's sum of all of its friends. So we are introducing dq to represent a small piece of charge, but then immediately trying to find a way to represent that amount of charge in terms of the geometry of our problem. So the dq is a temporary thing, but we know that we have functions that have dq in them. Right, this is how you would write Coulomb's law for a piece of charge in a region of space where you may have a collection of point charges or a distribution of charge. In this expression, dq represents just a point charge, but what we're trying to say is that if you want the entire electric field, you will have to integrate and sum up the contribution of every piece of charge. Is that answering your question, Sam? All right. Now, I did this one with a non-uniform charge distribution. The truth is, I'd like to do the next one with a uniform charge distribution just to make this easier. Are you guys all okay with that? So let's go back to what I wanted to start with, which is we're going to try and find the electric field at point P. And point P is located a distance A away from a bar of charge. And this bar of charge is length L, total charge Q. Good to go? Step 1. Identify a piece of the total charge. Just like last time, I'm identifying a piece of the total charge. Again, you decide, is it a piece of a line, a piece of a surface, or a piece of volume? I think we can treat this like a line of charge. It's got very good linear symmetry. Now, this is still part of step 1, but you should work out what the charge density is of your object. And the charge density will depend on whether you have some kind of linear symmetry or a linear object, a two-dimensional object, or a three-dimensional object. But it's going to be total charge over total size. So your size changes depending on what kind of object you have. We have something that's linear, so it would be total length. But if it was some surface, it'd be the total area. If it was a three-dimensional shape, it'd be the total volume. So our lambda is Q over L. We may never need lambda. Like we never may have to substitute lambda into the problem. But it's good to be thinking about the charge density for later use. Now, the next thing we have to do is we have to identify a way to point to the object. We've already done it for this shape, so I'm not going to spend a lot of time belaboring that, but you still have to find a way to point to this particular charge. This is where you identify where you're going to start and where you're going to end and where your piece is in relationship to that. So I introduce into the problem where I think a relevant place to call 0 will be. I'm going to use a Cartesian relationship, a one-dimensional Cartesian relationship, and say that my piece is located a distance x away. And since this is a linear piece of charge, I'm going to describe the size of that piece as being a little more in the x direction. These are all the things I already said just a moment ago, just repeating them. So this is a way to start. This is a circle. Well, you just pick a place to call 0 and find a piece of arc and find a way to point to that piece of arc. In every one of these cases, you need something that will help you decide geometrically where the first object is and where the last object is, and can you point to all of them in between? And here we can. Now, once you've established all of these things, your next step is to try and find a way to write dq in terms of the geometry. That's what we're doing next. We've got all the geometry set up. We've got relationships all set up. We have to write dq in terms of the geometry. And for us, that's almost always going to be a ratio. And we just talked about it a minute ago, but it's always going to be dq is to your shape, in this case dx, as the total charge is to the total length. This is the ratio we're talking about, whether we're talking about this in terms of a two-dimensional system or a three-dimensional system. Any one of these is helping you figure out a way to replace dq in your function. So you choose the one that works the best. You may have to use lambda, you may not. And also part of that depends on how many letters do you want to have to carry around during your mathematics. Obviously, if I use lambda, I'm carrying around fewer letters. But Q over L isn't particularly complicated. So I might find that having Q over L is reasonable. Now we're going to find the electric field first, and then the electric potential second. In dealing with the electric field, there are specific things that you have to do different than the electric potential. It does not matter if you use 1 over 4 pi epsilon naught or k. So it doesn't matter. So the only thing is, you do have to use what they tell you to use. So if they specify k or they specify epsilon, you have to use the one that they specify. But if they don't specify, your answer is just as legitimate if you use k or as if you use 1 over 4 pi epsilon naught. Electric field is a vector. Always be concerned about dealing with vectors and look to see if perhaps there's any symmetry you can exploit. Meaning, is there enough symmetry where the vector part cancels out or something? Obviously, there isn't in this case. We're going to get no symmetry. In fact, the worst thing about this one is I don't know that we can do this as a single integral. We're likely going to have to do this as a double integral because in this example, as in any example that involves an electric field, the electric field is going to exist in space in a direction. And based on what I have written now, this yellow line that connects dq with the point of reference in space, that yellow line dictates the direction of the electric field from that point. That yellow line is telling me that there's going to be an electric field contribution in the r hat direction. And this yellow line is r. So I now know that there's going to be an electric field that's this way. And unfortunately, you can look at the problem and note that every single piece of charge is going to contribute to an electric field that's in a different direction. So once you've kind of drawn in a picture, something that represents the direction of the electric field and gives you the specifics you need for your problem, we needed something to represent R. We've done so. That yellow line represents R. You need to ask, is there any symmetry that I can exploit in doing this problem? The answer is yes. What that's likely to do is tell you that you know the direction of the answer due to the symmetry. So if we were in the middle of the bar, there'd be symmetry. Meaning if the point was, say, right here in the middle of the bar, I probably won't care about the part of the arrow that's to the left. because I know that there's going to be symmetrically related contributions that will push it to the left and the right. So I can ignore some of the X components and only deal with the Y components. That's the part I mean when I say, is there any symmetry that we can exploit? Yeah.
If the point was in the middle, but it was non-uniform distribution, you still have symmetry?
You would not have symmetry. If it was a non-uniform distribution, you're going to have to do exactly what we're going to do here. So the AP exam definitely kind of presents, or I would say makes more of your problems symmetrical because it speeds up your work. If you can do the non-symmetrical problem, you can do the symmetrical problem. It might not be true vice versa, but they're really just looking to see if you can set this up. They're not as interested in you actually, committing to the math. This is non-symmetrical though. And because it is, that means you have to break this up into two different integrals. Now, how you break this up depends on what coordinate system you've chosen to use. We've chosen to use a Cartesian coordinate system, which means we will have to have DE in the X direction and DE in the Y direction. It's the only way to do it. Our math is one-dimensional, so if we don't have a way of using symmetry, we have to consider both directions. It's just like finding net force. You add up all the forces in the X direction. That's what we are doing here. Remember, this expression comes from Coulomb's law, which is a force. So we're just doing net force in the X and net force in the Y. But DE in the X direction, well, based on what I've drawn, that's the X direction. That's the Y direction. I see an implied angle. This is an implied angle. I'm going to put in a placeholder. This can't be in my answer, but I'm putting in a placeholder because I'm going to have to use that angle. I'm going to have to deal with the trig here. And because I have a placeholder, I'm going to use the placeholder everywhere I can and make everything relevant to the placeholder. I'm doing this because finding components means using trig. And for every time or every instance I use trig, I need an angle. You need to find a placeholder angle. But this means taking the whole portion of the electric field and multiplying by cosine or sine. In the X direction, it's going to be cosine. In the Y direction, it's going to be sine. That's because that's how I set up X and Y. All right, so we established how big our piece of charge is. We established a coordinate system to describe where it is. We have found a way to replace dq with something related to that coordinate system. And we have taken a look at our expression for the electric field and found a way to break it up into components in the X direction and components in the Y direction and look to see if we have any reasonable symmetry, and we don't. Your last portion here is to try and put everything that you have developed into an expression that's based on a single variable and the rest given constants. Okay, you got to get everything in terms of a single variable and the rest have to be given in terms of constants. For example, theta can't be in my answer. X can't be in my answer. These are constructs that I created and put into the problem. Even R can't be in my answer. The only thing that can be in my answer is going to be A, Q, and L. And the fundamental constants that I get to use, right? These. So all the other stuff has to be replaced. So let's start with, say, this one. I'm looking at DE, and I'm noticing I have R squared here. I'm not going to be able to have R squared in my answer, so I'm going to have to find something to replace it with. That one I think is pretty easy. So I think I can do that right now. I think I can start looking at my picture and realizing that I can write R as A squared plus X squared. I am working in a constant, A. I'm also working in something that is part of the geometry I established. I know X has to go from 0 to L, so working in X makes perfect sense here. So again, I'm trying to work in variables. I'm also looking to the future, and I know my integration is going to have to do with x. So working x in gives me a reduction in the variables that are there. It's probably going to make my stuff look more complicated, though. Now, that I can't do anything about. So dq over the square root of a squared plus x squared, but then I square it, so this is just going to be a squared plus x squared. All right, cosine theta. I think I can replace that too, right? There's some geometry here that allows me to replace cosine theta. Isn't cosine theta just going to be x over r? I'm just looking at the geometry. Do you guys see that? This is very typical. This is kind of how that works. We've done this kind of thing before. So I'm going to go ahead and replace cosine theta with x over r, but I know I have an expression for r as a squared plus x squared to the 1/2 power. There we go. Pretty close. Now this is going to produce an answer that is all in the x hat direction. I'm going to remind myself that this is just in the x direction. So this is going to give me this component to the electric field. So shockingly condescending. Ferociously condescending. I like that one. That one's pretty good. What do you think? What would be a better one? Abhorrently condescending. Wow. You're abhorrent, Mr. Shelton, and condescending. All right. We're almost there. The only thing left is we still have dq in there, but we have a means of writing dq in terms of x. So I think our last thing is to just, all right, let's go ahead and replace it. So I'll put the q over L right out there out front, and I can put just dx there. There we go. We took our original function. We've modified it to be in one dimension. We then went and replaced every single thing in there with a constant or our placeholder for position. All that's left is to tell the math where the first piece is and where the last piece is. First piece at 0, last piece at L. Now, I think this one actually can be, the calculus can be done, or at least can be done more reasonably. It looks pretty terrible, but let's get all of those constants out first. And if I look closely at this, I think this is what we have. I don't want to do the math. As I said before, I'm not going to do the math. But this is where it leads us, right? It leads us to this integral. What is the only difference between this one and this one? Sine theta goes to cosine goes to sine. If I look at my geometry here, what's sine theta going to be? A over r. So the only difference here is that instead of having an x here, I'm going to have what? A. Don't redo work. Although I know, and some of you know, that change makes a big difference in the math. Huge difference. One of these is going to be easy to find. One of these is going to be less so. Yo, calc people. I got people who win calc awards in here. Which one of these is easier to do? X or Y? You think? I think X you can use U sub. I think Y you can't use U sub, and you get a ridiculously terrible example of what you have to do. But the X one's not terrible because you can use U sub. Believe it or not, even if you did all of this work, this would not be the answer. But this is as far as physics gets you for the answer. What I mean by that is this is the physics involved in taking a charge distribution and getting a workable integral that could give you your answer. Right? The calculus does the rest. as does the Pythagorean theorem. When you're done with this, E in the x direction will be the result of that integral. And E in the y direction is going to be the result of that integral. You would use Pythagorean theorem to figure out the total, or maybe tangent to figure out the angle. AP doesn't want this to be what your test is about. Assembling this within the abilities or within the calculus of what they would expect you to do. Executing it, unlikely. They might do some things to reduce this. Providing symmetry reduces this. Providing perhaps one of these going to infinity reduces this. But the actual work to get here, not a whole lot you can do to reduce it.